I want to revisit the equation for voltage divider a little bit, because when we calculated it, we made a big assumption, big unspoken assumption that is important to highlight because it really determines whether your circuit will work or not. The assumption that we made is that R1 and R2, or whatever, how many resistors you use for your voltage divider, are in series with each other. So they are crossed by the same current. So for this example here, what that means is that the current given or taken by the central terminal is equal to 0. It doesn't matter what happened at this terminal or at this terminal. The one at the very top and the one at the very bottom can have as much current as they want because they're connected straight to a battery. So the battery will guarantee that the voltage stays the same. But the voltage in the central terminal is supposed to be 0. If that is not equal to 0, your equation is not valid anymore. You might wonder, well, is it that a problem? We'll just have to calculate a different equation. Well, let me give you an example. Let's say most of the time, that current in the central tap will be different to 0 because you're not using the voltage divider simply to create that V2 voltage, but your plan is actually to use that V2 voltage to do something. For example, let's say you have a battery voltage that is 4 volts and it's too high for your chip. So you have a chip that really needs 1.8 volt to work. So now you do your math to size R1 and R2, and you find out what is the value that you need to get 1.8 volt. After you've done that, you complete your circuit by connecting your chip. So the chips, usually they always want to be connected to ground. So they have a ground terminal, and then they have another pin, which is called VCC or VDD, which is the power supply. So now you connect it. The problem now is that this chip, in order to work, will need a current that is different than 0. If this current were to be constant, then you could probably live with it because you will be able to redo a different equation, considering that some current is stolen from R1 by this integrated circuit. And then you will have a new revised equation that tell you what is the value of R1 and R2 that you need to have 1.8 volts. That we say we want to have here. The problem with that is that chips, circuit, but in general, pretty much almost anything you can connect there. Problem is that the current that they need in order to work usually changes with time. It's not constant. If you look at an integrated circuit, in particular a digital one, the current that they need during the time will be something like this. It will keep changing really fast. It will go from 0 when the chip is not doing anything to a really high current when the circuit is like switching and doing operation. And the problem with that is that then you will have variable voltage across V2, and it's going to be really, really, really hard to guarantee that that voltage will stay equal to the desired 1.8 volt. Well, how can you solve the problem of a voltage divider where the central tap is actually using some current? Well, there are two ways to approach this. So the first way is don't use VT, the voltage divider, if the current is different than 0. So pretty much, this doesn't tell you much, but what I'm trying to say is that use the voltage divider only in cases where the current and the central tap is 0. So there are cases where that is true. For example, if you connect that to an input pin of a digital chip, the input pin most likely will have practically 0 current. So in that case, the voltage divider will work. Or for example, if you connect it to a comparator, or there are kind of some application that really truly requires 0 current. Or for example, if your goal is just to generate that voltage V2 for, I don't know, educational purposes, and the only thing you're going to do with it is just to connect a multimeter between the two terminals. So instead of having an IC here, you're just going to connect a multimeter to measure the voltage, then the current is basically 0. The second thing that you can do to have a working voltage divider is to make sure that the I bias is much bigger than the max of the absolute of I load. Now what I mean with that is the following. So the I load is the current that you need to have going into your load in order to do something with it. As I said before, you're most likely using a voltage divider to generate an intermediate voltage from the battery voltage, and you want to connect a load there. Connect a device, which could be a resistor, a chip, something that needs that voltage in order to work. So if we call this load, the current that this device needs is called I load. This current could be positive, negative. We cannot make an assumption now because we don't know what the load looks like. But we have to be able somehow to calculate what is the maximum absolute value that the current will ever had, either positive or negative. We need to know what it is. And if we can tell what the value of the maximum value of the current is, we can make sure that that is much smaller than I bias. And when I say much smaller, I mean at least 100 times smaller. So the I bias is the following. So the I bias is the current that goes through, actually let me represent it like this, that goes through R1 and R2. So obviously the current that goes in R1 and R2 is not exactly the same, but if we can assume that I load is much smaller than I bias, than the current going in R1, then the current going in R2 is going to be pretty much the same as R1, because from the Kirchhoff current law, you know that the current in R2 is equal to the current in R1 minus I load in this case. So if it's much smaller, it's practically equivalent to 0. So we can say that the current in R1 and R2 is the same. It's practically as if they were in series. And the value of the current across them will be simply given by V bar divided by R1 plus R2. So if that is the case, the equation that we calculated before still doesn't really apply mathematically. It's not perfect anymore. But because the amount of current that the load will steal from the voltage divider is really tiny compared to the one going down through the voltage divider, the so-called I bias, then we can pretty much neglect it. And we can say that the voltage V2 will pretty much always gonna be around the value that we designed the voltage divider for.